This video tutorial is a continuation of the walkthrough for heat exercise part 2. So previously we looked at the data on emergency department visits for heat stress illness, and we calculated both the proportions or percentages of people who ended up in the emergency department for each of these different groups. We then calculated the incidence rate, which is similar to mortality rate, excuse me, where we're dividing the people who end up ill by the population of that group who could end up ill. We contrasted the intra-group relative risk, meaning the comparison within a given group, to the intergroup relative risk, where we looked at that group's incidence rate compared to the incidence rate for the entire population. So here you can see I asked you to calculate the numbers, so I have them all calculated here. Your intergroup numbers should look the same as mine because we're using the same incidence rate for the population, but your intragroup numbers may look a little different because you have to decide which one is your comparison group. So just keep that in mind if you're looking at this and looking at your own numbers. And it's okay. It's up to you to choose who you want to make as your point of comparison. You just want to make sure that whatever you're using, it's consistent within that particular group. Okay, so one thing we didn't do in the last video is I asked you to do in the exercises to create graphs. This is just a way of visualizing and comparing the groups. So looking at the incidence rates, the original incidence rates, for example, we want to be able to make a graph of several different groups to compare them. So males and females, for example, if we want to look at comparing those visually, what we'll do is we'll highlight the incidence rates values and then hold the control key down and highlight the category names, so male and female. And with those highlighted, we can then insert a column graph, which is what we use, and we see this familiar graph. And so we'll put that on its own sheet, move the chart to a new sheet, and we'll call that morbid MF. All right, and this one should have a clear title. So we're looking at here. So we'll say this is the crude incidence rates of heat-related morbidity by sex, 2005, 2010. Okay. So you can see it's already got labels on it very nicely since the way we set it up. One thing we're going to do is we're going to compare different groups. So we'll do this for sex, and we'll also do this for, let's say, age. So let's go back to our data here. So again, the way it works is I highlight the incidence rate values and then hold the control key and highlight the labels that I'm going to use on the graph. Again, insert a column graph. We see that added there. And I want to move the chart to its own sheet. So we'll call this morbid age. All right. And we can see that nice label there. And again, we'll give it a label that makes sense. So this is the crude incidence rates of heat-related morbidity by sex, 2005 to 2010. All right. Now, if I want to compare this graph to this graph, right, it's important that they use the same range of values. So right now, the male-female, the sex one, it ranges from 0 to 50, but the age one ranges from 0 to 45. And so we don't want to compare them directly because they are using different ranges. So the way we can deal with that is to standardize it. So we'll format that vertical axis so that they use the same range of numbers. That way we can directly compare the height of the columns between those groups. Now we're going to do that for a couple other categories, or rather you're going to. Oops, jumped to the wrong one. So we did sex, age, and so I'd like you to also do climate, region, and urbanicity. And since we're going to standardize them so they all look the same, what we want to do is look at the numbers. So we want to look to see what's the highest number we'll encounter here. So we know that with sex it's 43 here, which was why we ended with 45 on the graph. Age, it's 41 here, so it's a little lower, it's close. But when we look at climate region and urbanicity, we see that climate region has up to 66.8. So that means that's probably the highest number. So we want to be able to allow for that. So since we're standardizing our graphs, what we'll do is we'll format that vertical axis by right-clicking on it, choosing Format Axis, and then in the bounds over here on the right-hand side, we'll change the maximum to 70, right? And that way, that'll allow room for the graph when we get to doing the climate region. And so when you do that, what's interesting is that it adjusts the heights, right? So now the bars look shorter. So we do the same thing for age. We'll format that axis and change its maximum also to 70, okay? And you'll see that it lowers the bars, but now because they both have 70 on their y-axis, the vertical axis, we can compare them directly, right? And so we can see, for example, that it's a little hard between the two graphs, but if you were looking at them on the same page, you'd see that the male incidence rate is higher than any of the age incidence rates. Now that's significant because it means that being male is a bigger determinant or more important source of risk than age. So that's an important conclusion. So what I'm asking you to do then is to construct column graphs for the other categories, climate and urbanicity, and again, making sure you adjust the y-axis and you can directly compare them. Now, all of that's going to show you the same thing. It's going to show you that that some groups have more risk than others, and that's what I'm asking you to distinguish, right? Not only to calculate it, but to look at that differences and to understand that that means that they're from the data we have that that group is at a higher risk. Okay, the last thing we're going to do in this part of the exercise is to do another statistical test. So when we look at risks like this, and we look at counts of numbers, right? The counts of deaths, for example, or counts of illnesses in this case. One common test that gets used is what's called a chi-square test. And the chi-square test is essentially a test that looks at the numbers that you have, in this case the emergency department visits, and it asks whether these numbers are higher than you would expect. Okay, and the big question is like, what do you mean by expect? Where does that come from? Well, in this case, if we look at sex, for example, male and females, right, and we want to know, okay, is the fact that you have more males in the emergency department, is that unexpected, right? And the simplest benchmark is to look at their proportions in the populations. So males were 67% of those who ended up in the emergency department, okay? Now, that may or may not be surprising. So one way to think about it is, well, what percentage of the population do males represent in general, right? Because if sex doesn't matter for this risk, then we should expect that if males are, for example, I'm just making up a number at this point, if males were 50% of the population, we should expect that they would be 50% of those who ended up in the emergency department. And if the actual number who end up in the emergency department is a lot different than that, then that's what kind of draws our attention. That's how we say, oh, there's something going on here. And so we have a formal test to be able to do that, which is this chi-square test. And the chi-square test works by building what's called a contingency table. And we're going to build that right now. So it's pretty straightforward, but you got to follow me here. So we're going to build it here, and I'm going to start it in this. It doesn't matter where you do it. This first part will be a contingency table of observed values. This is actually the data that we have in front of us, right? And so this table works by having the categories broken out by rows and columns. So we have the sex categories right here, and then what we have here is this is the contingency part of the kind of the cross tabulation. We have the categories about whether or not they ended up in the emergency department or not. So what I'm doing is I'm putting in the different possible categories that these groups can end up in. So for example, when we want to know is how many males from our population of males did not end up in the emergency department, okay? And so that we can figure out from the numbers that we have here by saying, okay, we're going to take the population, the total population of males, right? And we'll subtract out those who ended up in the emergency department, which is a number that we have, right? So we can see there that this is the number who did not end up in the emergency department, right? Which is the vast majority of them. The same thing for females. We take the number of females and we subtract out those who ended up in the emergency department, right? So that's the number who were non-ED, not emergency department. And then the total is just the sum of those two numbers, right? So this is just basically all the people who did not end up in the emergency department out of the total population, right? Now the number is going to vary a little bit from our numbers over here. So, and that's just because the way that I compiled the numbers, it didn't round properly, but it's not going to change our outcome very much. Okay, this part's easy. So the number of males who ended up in the emergency department, well, that's what we have here. So we can just copy over those values. Same thing with the females. We basically are going to copy over those. And again, we sum those values, right? So that number represents the total number of people, male and female, who ended up in the emergency department. Now over here, this is going to be the same concept. We're going to sum up values, but going horizontally. And this just represents the total population of males right there. Okay. And then this one, same thing over here. This number represents the total population of females, right? And then lastly, down here, we have the total population that we're dealing with. Okay. Again, there's a difference between the actual numbers we have here because of a rounding error I made previously. Okay. So in any case, this table represents essentially the data we have. This is what happened, the observed values. Now we're going to make a similar table down here of the expected values. So I'm just going to save time. I'm just going to copy this table here and paste over here, but I'm going to change the numbers inside the values. So I'm going to take these numbers here, okay, the ones in the middle, I'm going to take those out for the moment. And then this one is not observed values, this is expected values, okay. So it's a duplicate setup of the earlier table, but these are the ones that we should have gotten if all things were equal. So the non-ED that we expect is essentially going to be the proportion of the population that we think should end up in the non-ED. So let me make that clear. So if males, so what proportion of the population are males is the first question, right? So males are going to be essentially the so let's think of it this way. So if we want to calculate the proportion of the population that males represent, we're going to take that population of males, which is here, right? And we divide them by the total population, which is here, right? So that dividing the number of males by the number of the population will give us a proportion of the population that's male. So assuming that should determine how many of them are not in the emergency department, we can then multiply that by the total that we expect to be in the emergency department. So the ones who didn't, out of the population that ends up in the emergency department or non-ED, right? That's what we should expect, right? So again, the proportion of the population is male multiplied by the total population who did not end up in the emergency department. So we do the same thing for the females. We take the total number of females in the population, divide it by the total population, and then multiply it again by the same number over here, the total population who were not in the emergency department. Okay. The emergency department numbers, similar thing. We take again the total population of males as a proportion of the total population, multiply it by the total number of people in the emergency department. Okay. So notice that we're kind of assuming we're taking the number of people who end up in the emergency department for granted, right? But we're just saying who should they have been. And we do the same thing with the females. We take females as a proportion of the total population, and we also multiply it by the number of emergency department visits, right? And so what that means is that the totals don't change, right? What changes are the numbers in the middle, right? Because these numbers represent what should have happened if, their numbers were reflective of their proportions of the populations. So now that we have these two tables set up, the observed values and the expected values, now we're ready to perform our test. And so the chi-square test is really easy. So I'm going to put over here chi-square test, right? And so this formula starts with CHI-SQ, and you'll see that one of your options is the chi-square CHI-SQ.test. So we'll take that one. And so you can see what it's expecting now. So this is actual range and expected range. So the actual range is going to be the values that we observed, right? So that's that table right there. And the expected range is going to be this value right here, these sets of values, right? These are the things that we think should have happened if the numbers operated by the proportions instead. So we close off, and that's basically all the formula needs, and then we just hit enter, and then nothing mysterious happens. Let's open up that decimal number just to see. There's nothing hiding there. Okay, nothing. It's like a lot of zeros there. You could keep going until you hit something, but this is all we need. So this is a hypothesis test, and we've talked about this before in class. So recall that in a hypothesis test, in a statistical hypothesis test, you have the null hypothesis, which is the thing you're trying to decide whether or not to reject. And the null hypothesis is always that there's nothing going on here. There's no significant difference in this case. So that's what we're testing against. So the question is it safe to reject the null hypothesis that there is no significant difference between the groups? Because that's essentially what we're looking at. We're trying to decide whether or not there's a statistically significant difference in terms of the numbers between males and females. Is it like more than we would expect, right? And as you might recall too, when we do these statistical tests, the typical threshold is the 95% or the 5% threshold, depending on how you want to look at it. In this case, what we want to see is if there's less than a 5% chance that we would be wrong to reject the null hypothesis that there's no statistically significant test, then we reject the null hypothesis. If it's more than 5%, then we don't reject it because it's too high of a risk of being wrong. So in this case, as you can see by looking at the string of zeros, right, this is well below, because where would 0.05, it would be 0.05, right? So it's less than 0.05. So that means there's a very small chance that we would be wrong to reject the null hypothesis to say that there's no statistically significant difference. So the provisional conclusion is that this difference between males and females is more than expected. So there's definitely something going on here that's interesting. So we say there's a statistically significant difference between the two groups. So if we wanted to, we could repeat this analysis for each of the groups to look at to see whether those differences are statistically significant, to tell us that there's something interesting going on here. So that's it. So that's the last bit of heat exercise part 2. So make sure that you've constructed the remainder of the graphs that I told you about, and also that you check your numbers to make sure they're coming out properly with the formulas. All right, and I will see you in the next exercise.